In this simulation, we are going to be able to make some waves. So if I grab the end of this rope, the disturbance travels at the characteristic speed of sound down the rope. And frequently, we deal not with random perturbations, but with periodic oscillations, usually in a sine wave pattern, as is done here. Each point on the rope is oscillating periodically, and they're all oscillating with the same frequency, which is the frequency that this motor is oscillating with. In this case, it's oscillating with a frequency of 50-something. And so frequency F is the number of oscillations per second. And so it's measured, since this is a number, in units of inverse second, and once per second is called a hertz, which is why the frequency of your radio signal is measured in megahertz if you're listening to FM radio. And so I can restart this oscillation, and what we see is that because it takes a longer amount of time for the wave to get farther down the string, the position of the string here reflects what happened here a longer time ago than the position of the string here. And so the periodic oscillation of the driving force causes each point on the string to go up and down. Notice the wave is moving, the string is not going anywhere. But also what it causes is, because distance translates to time, we get a periodic sinusoidal structure in space at any given instant. And that is characterized typically by the distance between subsequent peaks, the distance along which the wave repeats. That's its wavelength lambda. And if you think about it, sitting at some point for a second, F peaks will come by, and so F peaks will come by. That means the wave will have transferred a distance of F times the distance between peaks. In other words, F times lambda is how far the disturbance travels in a second. So F times lambda is the speed of the wave, which we characteristically call c. Now, the reason we're dealing with periodic oscillations is a complicated mathematical theory called Fourier analysis that says any deformation can be written as a sum of periodic ones, but Fourier analysis is not some abstract mathematics. It's exactly what our ear does. When your ear hears sounds, it analyzes them into a sum of harmonics, and you hear the pitch of a sound you hear is given precisely by its frequency, and you can hear three different notes and distinguish that there are three notes there. This is biology and not physics, but it is definitely true, and I can increase the frequency, and what we see is that when I increased the frequency, the wavelength became correspondingly smaller. The frequency times the wavelength is a constant, the speed of the wave. A wave is characterized, therefore, by its frequency or its wavelength, given the speed. Those are related, but also by an amplitude. An amplitude is simply the magnitude of the largest deformation. So an amplitude of 17 is a very small deformation, and an amplitude 3 times as large is a very large deformation. So periodic disturbances, as we saw, are characterized by their frequency f in hertz, the number of cycles per second. If a wave is traveling at a speed c, a periodic disturbance will produce a periodic wave in space at any given instant with a wavelength lambda that is related to the speed by this important relation. Lambda wavelength times frequency is equal to the speed of the wave. The wave is characterized also by the amplitude, which is the maximum amount of the perturbation. And one of the important things about waves is the string didn't move, but clearly waves carry energy from one place to the other. You can imagine hooking something at the other end of the string. I will vibrate this end, the wave will carry it and cause that object to vibrate, giving it kinetic energy. That kinetic energy came from my hand, and therefore a wave carries energy. In fact, it carries an energy, if it's periodic, per unit time that is constant. Over time, energy is flowing down the string, and so you measure an energy flux in joule per second. A joule per second is known as a watt. This is the same unit of energy per unit time that you measure the intensity of your light bulbs in. How much energy does it take to operate that light bulb for a second? Now, this is a wave on a string. Of course, a wave, like a sound wave that travels in 3 dimensions, will carry an energy flux that is a density, because if the wave is propagating over a wide front, each bit of the wave carries an energy. So we measure the flux in watts per meter squared of wave front, and that energy flux in watts per meter squared is proportional to the square of the amplitude. Clearly, the larger the amplitude, the more energy the wave is carrying, and the flux is going to be measured in watts per meter squared. Now, what happens when 2 waves meet is a very important property of waves. Let's look at it in a demo, and then we'll talk about it. In this demo, we have a loudspeaker. The loudspeaker will be creating a periodic wave, and we see the wave fronts are shown in this picture. They spread away from the loudspeaker, and what we see here is a measure of the pressure or the density, the perturbation that the wave represents at one given point, and we see the characteristic periodic oscillation that we're talking about. And one thing you can see is that unlike waves on a string, we'll talk about this, but because these waves are spreading out, the amplitude of oscillation is larger near the source than it is far, and anybody who's stood very near a honking car horn is painfully aware of this fact. We'll talk about that aspect of things in a little bit. I just thought I'd point it out while we're seeing it. But the interesting thing to note is what happens when instead of 1 loudspeaker, we put 2 speakers. So now the 2 speakers are both creating wavefronts, and we see here what happens as the wavefronts add. And you notice that I've put my detector in a very interesting point. The 2 speakers together, each of which would have produced the noise with the amplitude we saw before, produced essentially 0 noise at the position of this detector. But if I move the detector a little bit, I will see that it's not because the 2 speakers are not producing noise at all. I see that, indeed, at this position, they're producing a far louder noise together than either one separately, or in fact, more than twice the sound that each would have produced separately. Somehow the combination of the 2 speakers is focusing sound into these regions where the dark bands are, and leaving these regions where the gray bands are, the nodes, where essentially no sound gets to. Now, the reason that this is possible is because waves can subtract from each other. When these 2 waves propagate, it turns out they essentially don't interact with each other at all. That's the approximation that we're working in, and it's a valid one for sound waves. And what that means is that the total perturbation at any point in space and time is the sum of what it would be if there was 1 speaker and what it would be if there was the other speaker. And how does that, adding what 1 speaker would produce to what the other speaker would produce, lead to 0? Well, remember, they're both oscillating at exactly the same frequency. So there can be a point where, because of the time delay from this speaker being different from the time delay from that speaker due to the difference in distance, when a peak from this speaker reaches, it is always timed to arrive at the same time as a trough from this speaker, so that the 2 waves that these 2 create are always counteracting each other. Waves add, but that addition can amount to subtraction, and that phenomenon is known as interference, and it's characteristic of waves. So let's summarize what we've learned here. A hallmark of wave behavior is that waves are deformations or perturbations to some equilibrium, and when 2 waves meet at the same point in space and time, the 2 disturbances add. In other words, each wave behaves as though the other were not there. We just add the disturbances. What this allows, if the waves are of the same frequency, is that if the time delay between one source and the other source relative to your position is suitably adjusted, in other words, the distance difference, which translates to the time delay, is suitably adjusted, you can adjust it so a peak from one wave precisely meets a trough from the other. The 2 waves add in the sense that they subtract, and you can get nodes, you can get regions of quiet in the vicinity of 2 speakers producing the same frequency. This will be important to us. It's a hallmark of wave behavior. Now, another property of waves that is going to be useful to us, is extremely useful, in fact, is something called the Doppler effect. It's the well-known phenomenon that the sound from a moving source sounds different than the sound from a stationary source. If a source of noise is approaching us, it sounds higher in pitch than were it stationary. If it's receding, if it's moving away from us, the pitch sounds lower. The archetypical example of this is the sound of a race car driving past you. I'll play it in the speakers, perhaps you can hear it. That whine is the transition from an elevated pitch as the car approaches you to a decreased pitch, decreased frequency as the car recedes from you. And the mathematical formulation of this is due to Doppler in the 19th century, and we can understand this rather straightforwardly. Here is a source producing regularly spaced periodic waves, and an observer placed over here receives the waves with a time delay. It takes time for each wave to reach there. The time delay is the same for each wave, so the time between subsequent fronts is the same as the time between subsequent emissions, and this is a stationary source. The frequency with which his ear is oscillating is the same as the frequency with which this source is producing the sound. That is true. Now let's move on to the case where the source is moving, and let's again place our observer over here, and we see that what's going on is that the wavefronts appear compressed on this side. They're compressed, of course, because between the emission of one wave and the next, the source moves, and so the distance between the wavefronts, as seen by the observer here, is smaller than it would be were the source stationary, and we can easily compute the relation between the two, because the distance between subsequent wavefronts as they arrive at this observer, lambda, which is the wavelength that this observer sees, is equal to the distance between the two wavefronts when they were emitted minus the distance which the source traveled, because each subsequent wavefront has a shorter distance to travel, because in the interim between emitting one wavefront and the following, the source traveled a distance given by v times the time between wavefronts. What's the time between wavefronts? The time between emissions is 1 divided by the frequency, because this is a number of seconds. And so remembering that lambda times f is c, I can write f as c over lambda, and I get lambda is lambda 0 minus, let me write this correctly, lambda is lambda 0 minus v lambda 0 over c, or Doppler's formula, lambda is lambda 0 times 1 minus v over c. Notice that this v was taken to be positive when the source was approaching the observer. An observer on this side, of course, sees the wave dilated. The wavelength looks longer. The pitch is lower as the car is receding from you. Each subsequent wavefront has a longer distance to go. That is compensated in this formula by considering v to be negative if the source is receding and positive if the source is approaching you.